Okay, so today we're going to be looking at the properties of exponential functions. So let's take a look at our warm-up. We're asked to evaluate y equals 2 to the exponent x. And so I'm going to just substitute in the different values of x that I have here into the equation y equals 2 to the exponent x. And let's just take a look at what's happening in this example. So for the first one, I have y equals 2 to the exponent negative 5. And I know from my experience with negative exponents that I would need to write the reciprocal of the base to a positive exponent. So the reciprocal of 2 is 1 over 2. And so a positive exponent would make it 1 over 2 to the exponent positive 5. And I can evaluate this to get y equals 1 over 32. And I'm going to continue to do the same with the rest of the problems. So I have y equals 2 to the exponent 0. And from my experience with zero exponents, I know that any base raised to a zero exponent gives me a value of 1. And let's try the next one. Y equals 2 to the exponent 2. That's easy. Y equals 4 is my result. And the next one, y equals 2 to the exponent 5. So just replacing x with 5. And 2 to the exponent 5 is equal to 32. So the pattern that I'm noticing here is that as I increase the value of x, as I go across, the actual value of y is also increasing. And that's because I'm taking the base and I'm multiplying it by itself more times. So if I multiply 2 by itself twice, I only get 4. But if I multiply 2 by itself 5 times, I get a larger value, which is 32. Now let's take a look at the next one. We have y equals 1/2 to the exponent x for the values of x that are listed here. So let's substitute in again. So I have 1/2 to the exponent negative 5. And again, negative exponents, so I'm going to write the reciprocal of the base, which is 2 over 1, to a positive exponent, which is 5. And so I get, that's like 2 to the exponent 5, which is equal to 32. Take a look at the next one. So y equals 1/2 to the exponent 0. So notice that I'm putting in the base of a half in brackets, since the exponent of 0 is being applied to all of it. And again, any base with the 0 exponent gives me a result of 1. Let's try the next one. Y equals 1/2 to the exponent 2. So one of the exponent rules that I remember is that when you have an exponent being applied to a fraction, that exponent gets applied to the numerator and the denominator. So this 2 is actually being applied to the 1 and the 2 at the top and bottom. So another way of writing this is y equals 1 squared over 2 squared, which gives me y equals 1 over 4. Okay, let's do the last one. 1/2 to the exponent 5. And again, 1 to the exponent 5 is 1. 2 to the exponent 5 is 32. And this time what I noticed in my pattern of values is that as I go across, the value of x is increasing again. So from negative 5 to 0 to 2 to 5. But this time the value of y is actually decreasing. So I'm starting with a high number, which is 32. Then I go down to 1, then to a quarter, and then to 1 over 32. So my y values are actually decreasing. And in case you're wondering why that happens, our function that we're looking at is y equals 1/2 to the exponent x. So what that means is, this is sort of like y equals 1 to the exponent x, which is just 1. It doesn't matter how many times you multiply 1 by itself, you still get 1. Over 2 to the exponent x. So essentially what's happening is, I'm multiplying the base by itself a bunch of different times. And as I multiply the base more and more, the base gets larger, and 1 divided by a really large number gives you a very, very small quantity, which is the reason why we have a very small quantity when we plugged in a really large exponent here. Okay? So 1 over 2 to the exponent 5 gives you a really small number versus 1 over 2 to the exponent negative 5, which is the same thing as 2 to the exponent 5, which gives you a much larger value. Okay? So it's the fact that the base is getting larger that makes the actual function get smaller.